Okay, so this is a very important topic, which is Lucas's theorem. It's a very, very important theorem, especially if you do finite groups. But it's a very basic computation, really, because most of us have seen permutation and combination. But this is just a way to take a combination modulo a number. Okay, I'm going to explain what all that means. But before we begin, let's just see what Lucas's theorem says. So if you have a prime P and M and N are non-negative integers, then these numbers have a base P expansion. So essentially you can write M as M0 plus M1P plus and so on MKP to the power K. The same thing for N, you can write N in base P. Base P expansion of N is this. The condition here is that Mi's and the Ni's are numbers greater than or equal to 0, less than or equal to P minus 1. In fact, because we require both of them to end at P to the power K, means that for some of the NKs or some of the MKs would definitely be 0. Okay, but what the theorem says is that if you want to compute M combination N, so M choose N, that this is equivalent to the product of Mi, so this Mi choose Ni, so the product of this for I going from 0 to K modulo P. So these two things are equal modulo P. And so the task here is really to prove this important theorem. But before I actually go into proving it, it would be nice to compute sort of an example so you can see. So let's say M is 14 and N is 5. So 14, as you can see, so the highest power of 3, so we're looking at base 3, base P is 3. The highest power of 3, which is less than 14, is 2, so that's 9. So there are only 1 9s in 14, so we have 1 times 9, the remainder would be 5. Well, the highest power of 3 less than 5 is just 1, so you're going to have 1 3, and then so now you have 2 left, so this is just 2 times 1, which is 2. If you go to 5, the highest power of 3 dividing 5, the highest power of 3 less than 5 is just 3 to the power 1, so that's why you have 1 here, and then what you have is 2 left, so that's just 2 times 3 to the power 0. So as I mentioned before, because I want both of them to end at the highest power here, 3 to the power 2, you have to complete this one by adding 0 here to 3 to the power 2. Now, what the theorem was saying is that if you do 14 choose 5, so 14 combination 5, that the answer is congruent to 1 mod 3. And this is because it's saying it's equal to the product of this, it's product of M combination 1 and the N1 combination 1, sorry, 1 combination 0, 1 combination 1, and 2 combination 2, which is all, these are just 1. So this answer, 14 choose 5, is equal to 1 mod 3. And of course, you can check this with your calculator. You can just compute 14 combination 5, and you see that the answer is indeed 1 mod 3. Okay, so that's it. That's how this works. So let's go back. So that's the theorem we're trying to prove here, and the way we prove this theorem is using group actions. Again, as I mentioned earlier, this theorem is really important when you're trying to, when you're doing finite groups, especially when you are proving Syllo's theorems. The first Sylla theorem requires the use of this result. Of course, there are many ways to prove this result, but this is the way that I found elegant, and it's a good application of group actions. So let's get into that. Okay, what is a group action? Well, if you have a group G and a set X, a group action is just a map from G cross X to X. So essentially, it takes an element of the group to an element of the set X and gives you a new element of the set GS. Well, it could be a new element, it could be the same element X. But as you take a group element and an element of the set, and you get an element of the set. So you can think of it as a map from another way to think about group action is a map from X to X. Okay, so the group acts as morphisms from the set S to itself. Okay, anyway, so it's a map from G cross S to X, where G comma X gives you this element here. And this has to satisfy the following condition. If G is the identity element of the group, then what you get here is just X again. So yeah, another way to say it is that the identity element acts as an identity. So the action it does nothing. Okay, it just gives you back X. And then the other property here is that if you first act on X with H, and then act on whatever you get here, HX with G, then this is the same thing as first combining GH in the group, then acting on X. Okay, and this is true for all of G in GH in G and X in X. Okay, so again, whether you combine G and H in the group first, and then this is an element of the group and you act on X, the result is the same thing as first acting with H, and then whatever you get now, this is an element in X, you can act with G. So if you have such a map that is satisfying these conditions, then we say that the group acts on the set X. So let's do some example. If you take any group and you take itself as X, so the group is G and the set is G as well, and the action is by left multiplication. So if there's an element of the group, the element G acts on S by just multiplying this. So this gives you, of course, a new element of the group because the group is closed under the operation in the group. So this action, so let me go back here. So this is not multiplication, by the way. This is just the way we denote the action. The action could be anything. Okay. In this case, the action here is just the left translation by the group element. So you get this new group element. Another kind of group action, and you can show, of course, that this is a group action. If G is the identity element, you get the identity. So you just get X here back. So it satisfies the first property. And the second property just comes from associativity of groups. So if you have two elements, GH, then act on H, act with H first, and then act with G. It's something as combining GH in the group and then acting, so that works. Okay, so remember this action, we're going to say it again. Another action is conjugation. So a group also acts on itself by conjugation. So if this is an element of the group, and this is a group G, the action of G on X is just conjugation. Again, you can see that if G is the identity element, you get back X here, so that's satisfied. And you can see that if you conjugate by H and then conjugate by G, it's something as conjugating by GH. So again, this is a group action, conjugation. And then for a more geometric action, think of a regular n-gon, and this the dihedral group Dn is just acting by reflections and rotations. And you can check that, in fact, this is a group action as well. Okay, so once you have a group action, you can define this set here, which is called the orbit of X. So if you pick any element in your set X, you can define the orbit of X under the action. This is the set of images of X under the action by G. So where, so all the possible values of this as you run through G. That's what we call the orbit of X. Okay, it's a subset of the set X. Now the stabilizer here of element X is now a subset of the group. So it's a set of elements in the group that fixes X, so that kind of behave like the identity element. Okay, so the identity element, if this identity element, you're going to get X again, but sometimes it's not only the identity element that behaves like this. So the set of elements in the group that fixes X is called a stabilizer of X. It's an easy exercise to show that the stabilizer is not just a subset of G, it's actually a subgroup. Okay, so I'll leave that as an exercise for you to try to show that this is a subgroup of the group. Okay, so you can ignore this here and just focus on. I think I need to rub that off. So ignore this. This is a theorem. Okay, so the theorem is that if you have a group acting on a set X, if you have a group acting on a set S, then for each S you have the orbit as we have defined before, and then the collection of all the orbits forms a partition of the set S. So you can partition the set into orbits. So this is a proof. So the proof is really to show that the relationship of being okay. So the final relation X is related to Y if there exists a G such that Gx is equal to Y. So essentially it's saying that X is related to Y if they are in the same orbit. Okay. So you can see that there is a G such that G times G acting on S gives you Y. This will say, of course, you can now multiply it by G inverse here to show that both of them are related if they are in the same orbit. Okay. This is a reflexive relation which shows that X is in its own orbit. X is in the orbit of X. And then this is the symmetric if G is related to, if X is related to Y, then Y is also related to X. And then it's transitive if X is related to Y and Y is related to X, then X is related to Y and Y is related to Z, then X is related to Z. So that's a transitive property. Now, if you have a relation that satisfies these three properties, then that gives you an equivalence relation. So that means you can partition the set S into these equivalent classes, and these equivalent classes essentially what we call orbits. Okay, so that proves this theorem. The way to see it is just pick an element, and see the orbit by acting on it by all the elements of G. Once you have exhausted the elements of G, then that orbit is complete. Then you pick another element as well, and then continue that way. And this theorem is telling you that if an element is equivalent to X is equivalent to Y, Y is also equivalent to X. So it's either if two orbits intersect, then they are equal. They are the same, because it means that there is one element which is in this orbit and it's also in that orbit. But if it's in this orbit, it's equivalent to every element in that orbit. If it's also in this other orbit, it's equivalent to all the elements in that orbit. And then you use this property here of being transitive and conclude that these two orbits are exactly the same. Okay, so now that takes us to the very important orbit stabilizer theorem. So if a group G acts on a set X, then for every element X in X, the size of the orbit is just the index of the stabilizer in G. Okay, if G is a finite group, what we mean by index is just divide it. Remember, the Lagrange's theorem tells us that the order of a subgroup always divides the order of the group. So, and that number, so when you divide the order of the group by the order of a subgroup, we call it the index. Okay, of course, if G is a finite group, we can write it like this. But if G is not a finite group, then it doesn't make sense to write it. So what we call it is the index. Okay, so the size of the orbit of X is just the index of the stabilizer G in G. And this is not difficult to prove. To prove this, you can define, so what you can do is to define a map. So this is just the number of cosets. So this is the number of cosets of the stabilizer of X in G. That's the subgroup. This is the subgroup here. You take the coset of G coset of the stabilizer in G, and you count the set of cosets, how many elements are there, and that's what we do. So we claim that the coset, the map from this coset is the same as the size. So the size of this coset, so the number of elements in this set here, set of cosets, is the same thing as the number of elements in the orbit of X. So we define this map phi, which takes a coset, so it takes a coset to this element of X. So G stable, so this is a coset of G, and then this is just the action of G on the element X. We claim that this is a well-defined bijection. So well-defined means that if I choose, if two cosets are equal, then their images should be equal. So these two cosets being equal means that there is an element in the stabilizer of X, let's call it S, such that there is an element in the stabilizer S, which is S, such that H is just equal to G times S. That's what it means for these two cosets to be equal. That means H is some G times S, because H belongs to this coset, and since these two cosets are equal, H also belongs here. But every element here is just G times something in the stabilizer, so that's why we have that. So now we want to show that their images will be equal. So from here, the image of this is going to be image of this is just G. So it's just Gx, and the image of this is Hx. But Hs, by definition, H is equal to Gs, so it's equal to Gs times X. But S is in the stabilizer, so S times S. Remember the property of second property that makes group action is that this is the same thing as that. So S times S acting on X it's a stabilizer, so it's just going to give you X back, and then you get Gx. Okay, so this shows that Hs is equal to Gs. Their images are equal. So that shows that this map is well defined. Injective, so suppose that phi of this element is equal to phi of this element. What it means is that G1.x is equal to G2.x. So you can multiply on both sides by the inverse of G2, so that gives you that G2 inverse of G1x is equal to x. So G2 inverse G1 is in the stabilizer, and of course that means that this G1 stabilizer, these two cosets are equal. Okay, finally, for surjectivity, we just have to prove that there is, if you give me anything in the orbit, so if you give me anything in the orbit, so anything of this form, I can produce a coset which maps to it. And that's very easy. So suppose if for any y, if you have y here, that means y can be written in this form for some g, then take the coset g stab gx, that gets sent by the map to that. Hence, we have a bijection, so that proves the orbit stabilizer theorem, that the size of the orbit is just the index of the stabilizer in G. Okay, so let's give some, this particular group action we mentioned earlier, which is the group acting on itself by conjugation. So that's conjugation. The orbit, remember the orbit